So we watched that introductory video about mass spectrometry. So what does mass spectrometry tell us? We know it's the third and final technique in our toolkit for determining the structure of a molecule. So IR tells us functional groups and types of bonds present. And we know C13 NMR tells us how many carbon environments we've got and how those carbons might be connected. And today, mass spectrometry will tell us the molecular mass. If we look at that parent ion, that'll tell us the mass of the molecule. That's really helpful. It'll also tell us the sizes or the masses of little fragments that break off when we fire that beam of electron at that molecule, right? Because not only does it knock off an electron to make the molecular ion, but it further shatters or fragments that molecule into smaller pieces as well, which we can weigh in the mass spectrometer. So here's a diagram of what we saw in the video. There's roughly 3 sections. In the first section, you ionize and then fragment your sample molecule. And then it accelerates and is deflected by magnets and around the bend there. And the reason why the bend is so important is because only masses of a certain size will successfully make it around the bend when you apply a specific magnetic field strength. Because if I rolled a bowling ball down this table here and towards Timmick, and Oscar, you were trying to save Timmick from it, you would want to push it that way, right? Push it away from Timmick towards Solomon. Yeah. So you'd have to apply a certain amount of force, right? A certain amount of energy you'd have to input to push the bowling ball or divert its path, right? And that's easier to do with a smaller ball with less mass than like a bowling ball. So my point is that different molecular sizes won't make it around the bend. If it's really heavy, you need a large field strength to cause that large molecular ion to successfully deflect and reach the detector. But we can change it. We can change it. And when you insert a sample, you alter that field strength during the scan of the sample. So you start with a really low field strength, so only the small, really lightweight ones make it to the detector. And then you increase the field strength to force more of those heavier ones to make it around the bend. So you're constantly vaporizing and ionizing samples, and as you scan through it, different parts of those samples will make it through to the detector to detect those different sized fragments during a scan. Cool. Remember, on the y-axis of a mass spectrum here, we're going to see the abundance, so how much of that ion there is. And that's determined by the stability of the fragment. Later today, we're going to look at how stable these different fragments are, because the stability influences how much we'll see in our spectrum. So in that first phase, when we ionize and fragment a sample, what we're doing is we're ionizing by firing a beam of electrons at a molecule in the gas state. So that's represented by M for molecule. We have an electron, and what it's doing is it's knocking off an electron belonging to the molecule to ionize it, to make a cation. And so we can see as a product, we have 2 electrons because we have that incident electron beam plus the electron it knocked off the molecule. So we have 2 electrons as our product and our molecular ion, right? And in organic chemistry, you've heard me refer to carbocations once in a while. It's an odd electron radical cation. So it has an odd number of electrons because we just removed 1 rather than a pair. So we call that lone electron a radical. And it's a cation. Cool. So here's a little friendly diagram that shows what's happened. We got a smiley face representing the high energy electron. That's what electrons look like, in case you didn't know. Did Greg ever teach you that? Yeah. No? Okay, cool. So in it comes, it's going to break that bond, and that bond says, oh no, I've fragmented, but it needs to lose an electron further to form a cation fragment. Cool. Look at the other fragment. Notice how it's not a cation. So when you fragment a molecule, one chunk of it becomes a cation, and the other chunk retains an electron and doesn't have a charge. So if we have a molecule that we fragmented, what's the detector going to detect? Is it going to detect both fragments? None of them? One of them? And why? What do we think? What do you think, Timmick?
We could detect the ion because the ion will be deflected by the magnetic field, while the ionic arc will just go straight.
Perfect. you're suggesting that charged things are obviously influenced by magnetic fields and neutral species aren't. So this neutral one is like an immovable bowling ball. If I pushed it towards Oscar, he would not be able to move it because a magnetic field cannot interact with a neutral species, a neutral fragment. Cool. But here, with that charged fragment, it will. That's what we detect. We detect charged species. So we can see the cation fragment we do detect. Cool. Now, we've formed our molecular ion. A few things you need to know when you look at a spectrum is that for all organic compounds containing only carbon, hydrogen, and oxygen, the molecular ion will always have an even mass number. This is really important to remember. Why is it important? Because in the case that you might have an amine or an amide or something, if a compound has a single nitrogen, that molecular ion will be odd. That's a huge clue about whether you have a nitrogen-containing compound or not. Cool. And as was implied in the video, if we continue bombarding the molecule with electrons, not only do you form that molecular ion, but the electrons do a great job breaking bonds within the molecule to get smaller chunks. Cool. Now, when we're looking at detection, the molecular ion, because it's the heaviest that the molecule can be without, adding anything to it, which doesn't happen in mass spectrometry, it's to the furthest right on the horizontal scale. So on the horizontal scale, we have the mass to charge ratio. Now, with most mass spectrometry, we're only forming ions with a charge of 1. So in other words, as they also said in the video, the horizontal scale is simply the mass, or how heavy that fragment is. Or you can just think of it in terms of mass rather than mass to charge, because at this level, we're only looking at mass spectrometry that forms fragments with a charge of 1+, nothing more than that. So if the molecular peak is at 72, that tells us the molecular mass of our compound is 72 grams per mole. So if we add up all the masses of carbons, hydrogens, and oxygens that we think are in the molecule, it better add up to that number. That's how you can check your work in problems that we're going to do, where you're going to propose a formula for the mystery structure, and it better add up to the weight of that molecular ion. Cool? So that's the most important thing we can use this for, is to check our formula against the molecular ion mass. Now, the other type of peak that we give a name to is called the base peak. And the base peak is the highest peak that you see on the spectrum. So in this spectrum, it's at 43. It's the highest peak on there. And they're all, their heights are in relative abundance, okay? So at 43, you can see across on the vertical axis, it's 100%. That doesn't mean all the ions have a mass of 43. It just means relative to the others. Let's arbitrarily call that amount 100%. And relative to that amount of fragments with a mass of 43, what are the relative amounts of the other species, right? So it's a relative abundance. That tells us, because the most abundant peak has a mass of 43, it's probably the most stable fragment. Remember, the more stable the fragment is, the longer it's going to exist before shattering into smaller pieces, right? So if it's really stable, we're going to see a lot more of it. So that tells us something about the structure for the fragment with a mass of 43 is particularly stable. Cool. So let's look at ion fragment stability. Like I just said, the more stable the fragment, the higher the abundance of it will be on our spectrum, and that's represented by a taller peak on the spectrum. Now, what influences stability? We're going to look at how the atoms around a carbocation can contribute electrons to stabilize that positive charge on the carbon. Because what influences stability is electrons helping to neutralize a positive charge on an atom. That will bring stability to the molecule. So if we look at the first row of molecules there, or of ions, I should say, where I've highlighted the red ionized carbon, in those three molecules, those carbons exist in what I would say is different environments, different things around it. You can classify them as primary, secondary, or tertiary, similar to alcohols and amines. So if it's tertiary, it has 3 alkyl chains bonded to that carbon. If it's primary, it just has 1 alkyl chain. So this first molecule on the left, would you call that primary, secondary, or tertiary? That one? Yeah, primary. Cool. And the one in the middle? Yeah, that's secondary. And then we have tertiary. We've got a methyl group and 2 other methyl groups on the side, right? So that's tertiary. Now, which of those 3 do you think contribute the most electrons to stabilize that ionized carbon?
Tertiary.
Yeah. Why do you think that is? There's just a lot of carbons around it, right? It's pretty easy. So we can see with the arrows there indicating the flow of electrons in the covalent bonds between carbons that they're able to be drawn towards that positive charge. So you have more contributions of electrons to stabilize the positive charge in a tertiary carbocation versus a primary where you only have one source of electrons to help stabilize that positive charge. So it's not entirely stable. It will fragment into smaller pieces. So if this was, if the primary carbocation caused a peak on your spectrum, it wouldn't be very high, and it would further shatter into smaller pieces you would see on the spectrum. Whereas I would expect the tertiary carbocation to form a pretty high peak. Not only that stabilizes things, but also really electronegative atoms that can contribute electrons. So if we're looking at this here in the bottom here, we have a carbocation bonded to an oxygen. That's a good source of electrons that can help stabilize the positive charge. Same with something like this amine over here. Remember, the nitrogen has a lone pair, and it can help share some electrons to help stabilize that charge. So nitrogens and oxygens can help stabilize the cations on the carbons. So let's do a quiz. Okay. So what we have are 4 quiz questions. Each question consists of a pair of molecules, and you have to tell me in that pair whether it's A or B that you think is likely to be most stable. So looking at question 1, A or B, just have a look at it. Which do you think would be the most stable? Think about the factors that increase stability. All right. Show of hands for A being most stable. Show of hands for B. Yeah, you all get it. Look at that. All right. What about question 2? Anyone want to suggest what they think here for question 2? Yeah. A looks good to me. It's a tertiary carbocation for sure, versus a secondary for B. Okay. Question 3. What do you think, Archie? Yeah. And question 4, Johnny?
Go.
It's a tricky one.
A again?
Yeah, because it's got that oxygen, right? There you go. There we go. Good job. Sweet. So we're fairly okay with that, eh? Predicting stability. Awesome. Now, here is a list of the common ion fragments that we see on mass spectra. So at this point, I'm going to hand out the 3rd and final poster from Compound Chem, listing the same sort of fragments we would expect to see. So you can see something that produces a peak at 15 is always a methyl group. Oh, did I give you extra stuff?
He has an instant gratification.
Yeah. Thank you.
I don't want 2 of them.
I like that you keep them all of them. You're the only one who has that.
Okay, so looking at the sheet here, look at the fragment. There's a picture of the fragment that causes the different molecular mass peaks. So at 15, we see it's a methyl group. Again, you see that the positive charge is there to remind you that it's ionized fragments with the charge that we're detecting, not the neutral fragments. So, okay, let's do a quiz to see. We can see at 17, it's usually an OH group. 28 is a CO group, 29 is an ethyl group, that's pretty common as well. Or it could be a CHO group, but usually it's an ethyl group. 43 is a really big one usually, 57. So you're going to see these numbers come up repeatedly in questions we'll do. And you'll notice that most of these fragments have an odd number as well, right? Most of them are odd. Cool. So we looked at that. Now, quiz for you. Take a minute or two to draw out the ionized fragments that would cause the peaks we see in this spectrum at 15, 29, and 43. So this looks like hexane. But what fragments of hexane causes peaks of that mass? Remember, carbon weighs 12, hydrogen weighs 1. Take a minute or two to draw them out, then I'll take up the answers. Very odd. I would guess that all the electrons would be stable. There's a difference here. There's carbon bonded to nitrogen oxygen where the plus charge is on the carbon. And so it's on the opposite. Same with like this one on the nitrogen, right? So I haven't looked into it too much. It'd be an interesting thing to find out which one's more stable. And the charges on the carbon or the electronegative atom bonded to it.
RJ. Is it more common with like OH and CO on this sheet? Is it because this is on the food or the just on the food?
They're looking at larger fragments and stuff. The smaller ones can like 17. Yeah. So like, make sure there were some extras on there. Okay. Are we ready to take up the fragments? Solomon, you're good? Sweet. All right. So the one at 15 is obviously just a methyl group. That's really what only thing it can be. 29 is a good old ethyl group. And then for 43, it's one of the 3 carbons in a row. So that's pretty easy, right? Sweet. It's good to recognize those. We will see them from time to time. And I propose, the formulas for those fragments, and I made sure to put the positive charge. I should have made it a superscript, but I couldn't do it at the time. So when you're writing it out, make sure you have the charges on your fragment formulas. Cool. All right. So we're going to do 3 last examples to wrap up this portion of the class, where I've got 2 spectra on each of these examples, and I'm going to show you how each molecule matches up with the spectra you see there. So what would you call that molecule on the left there? It's got 5 carbons, some sort of ketone. Yeah.
N-3O.
Sounds good to me. And what about the compound on the right? 4 carbons in the main chain. Yeah.
2-methyl-butane-3O.
No, the ketone takes priority, so you had a good beginning there, Solomon. But yeah, you said a 3-methyl-butane-2O. Yeah, that sounds right to me. Good practice with the naming. So let's look at the main characteristics. So the molecular ion peak and the base peak, right? So I've got those labeled on both. Cool. Now I'm wondering what causes some of these main peaks. So what causes the base peak? If we were to split the bond right there with the blue line there, we would see this fragment form, this ionized fragment. And yeah, if I count up all the carbons, hydrogens, and oxygens, it adds up to 57. That fragment's stable. It's bonded to the oxygen. Remember, that's one of the rules. Those electronegative atoms can help stabilize the charge. Cool. So that must be the fragment causing the base peak there. And the other fragment, the neutral fragment that's formed when we break that bond, is not detected, right? But it's proof that this is the ion we did form, because we can see the difference in mass between the molecular ion and the base peak is 29. And guess what? That weighs 29. So that's a good check. not only the fragment that we think is causing a peak, but the difference in the masses between peaks is also important. Okay, now what about the other peak there? Something around 29. That's simply if we ionize that peak instead. So, we have tons of molecules in a small volume of sample, and some molecules will fragment differently. So this peak at 29 is caused by this, the one in the purple box, being actually ionized and detected. Cool? All good? Sweet. Now, what about on the other side? We could break the bond there, forming two different ions with a mass of 43 each. So either one could be contributing to it, which explains why the base peak is so high. There's a lot of abundance, so both can form ions with a mass of 43. Now, there's a loss of 43 between them. Either one will be the neutral fragment, and the other one will be the charged fragment. There's a peak at 71, a small one, but it's there. And that's simply if we break off a methyl group, right? It looks like we're breaking off a methyl group, keeping the rest of the molecule, which has a mass of 71. And that's proof there that there's a difference of 15. Cool. So let's look at example 2. So from the IR, we know this is a secondary amine. Remember, we look at how many peaks there are for a primary versus a secondary amine. And we've got 2 of them here. We don't need to know how to name them at level 3, so that's fine. But let's look at the obvious things, so the base peak and molecular ion again. And let's figure out what causes the base peak. And I want you to help me figure out this part. So looking at that first fragment there, can you suggest a place to break a bond so that one fragment has a mass of about 58? Yeah, Solomon.
To the left of the nitrogen.
Okay. Looks good to me. Awesome. So we've lost an ethyl group. So theoretically, the difference between 58 and 87 should be the mass of an ethyl group. And that's on there. It's a mass of 29, so that's gone. So that tells us that's our neutral fragment. Good on you. There's a small peak at 44, and that could be caused by breaking the nitrogen-carbon bond on the other side. And there's a peak at 30, which is kind of a weird one, which I need to look into, because I'm like, how is that formed? Some sort of rearrangement, but you don't need to know that. Let's look at the spectrum on the right. There's a peak at 72. That's the base peak. So if we simply break off a methyl group, that will solve our problem there. And there's proof that the mass difference between the molecular ion and that base peak is 15, so we know that's proof that the methyl group was indeed the group that left. There's a peak at 44. Where do we think we can break a bond to form a peak with a mass of 44? Let's give that a go. Yeah, good on you. Awesome, Ella. Yeah, same as the other one. We know they're very similar. There we go. Cool. Now, last example we'll look at. So these are actually pretty simple alkanes, right? We got pentane and 2-methylbutane. Let's look at what the base peaks and molecular. I know. I combine the base peak and into beak. So base peak and molecular ions. Here's where they are. For the first one, where should we break a bond to form something with a mass of 43? Well, it's something like we just did, right? We want something with 3 carbons in a row to form an ion with a mass of 43. Cool. And the difference there is 29, so that's proof that we've lost an ethyl group. That's cool. And there's a small peak at 57. And that could be caused by just breaking off a methyl group. Cool. There is one at 29 just by an ethyl group charge fragment. Now what about the base peak at 43 on the other one? We could break a bond there, you can figure it all out, and so on. So we know that with something like this, we can propose where to break bonds to form ionized fragments that have certain masses to correspond with the peaks we see on a mass spectrum. So now I've got a few activities we're going to do to put this into practice. Sounds good?